Hello everyone, this is Dr. K. Evangeline Supriya working as an Associate Professor of Physics, Department of Humanities and Science, SRIT Engineering College, Anantapur, Andhra Pradesh. Today I am going to give you a video lecture on Engineering Physics Syllabus, Unit number 5, Semiconductors. A semiconductor is a material who will allow the flow of current partially. A semiconductor is a material whose conductivity lies between insulator and conductor. Silicon and germanium are the two best examples for the semiconductor. As you can see here, the solids are classified into conductors, semiconductors and insulators on the basis of the band theory, that is the width of the forbidden energy gap. So the valency band, what do you mean by valency band? Means the valency band correspond to the valence electrons present in all the atoms of the material is nothing but valency band. The energy band which is occupied within conduction electrons is nothing but conduction band. The distance between conduction band and the valency band is nothing but energy gap or forbidden energy gap or forbidden gap. So we are going to study semiconductors. So there are two types of semiconductors. One is insulators, one is intrinsic semiconductors and extrinsic semiconductors. Again, extrinsic semiconductors is divided into two types, p-type semiconductors and n-type semiconductors. So classification of semiconductors, intrinsic and extrinsic semiconductors. So extrinsic semiconductor, the semiconductor which is pure and having number of electrons in the conduction band equals to the number of holes in the valency band is nothing but intrinsic semiconductor. Pure silicon and germanium are the two best examples for the intrinsic semiconductors. In intrinsic semiconductors at 0 Kelvin, the valency band is completely filled and all the states and the conduction bands are vacant. So they act as insulators at 0 Kelvin. For silicon, energy gap is 1.2 electron volts and for germanium, energy gap is 0.7 electron volt. As you can see here, the distance formed between conduction band and the valency band is nothing but energy gap. This is a two-dimensional arrangement of bonding in silicon, because silicon is an example. Pure and silicon and germanium crystals are the best examples for the intrinsic semiconductors. And the energy gap at the intrinsic semiconductors at T is greater than 0 Kelvin, the valence electrons acquire sufficient some amount of thermal energy. As a result, breakage of voltage, breakage of covalent bond takes place, releasing free electrons. These free electrons creates holes in the vacant positions in the crystal. These vacancies are known as holes. At T is equals to 300 Kelvin, the energy gap of silicon is 1.12 electron volt and for the germanium it is 0.64 volts. As temperature increases, the width of the energy gap decreases and large number of electrons at the occupy the conduction band. Next one is extrinsic semiconductors. Impure semiconductors in which the large carriers are produced to impurity atoms are known as extrinsic semiconductors. Based on the type of impurity added, extrinsic semiconductors are divided into two types, p-type semiconductors and n-type semiconductors. N-type semiconductor is obtained by doping an intrinsic semiconductor with pentavalent impurity atoms like phosphorus, arsenic and antimony. The 4 valence electrons of the impurity atoms bond with our valency electrons of the semiconductor atom and the remaining 1 electron is the impurity atom which is left there. Therefore, the number of free electron increases as electrons are produced in excess. Electrons are the majority charge carriers in the n-type semiconductor and holes are the minority charge carriers. Since electrons are donated in this type of semiconductor, the energy levels of these donated electrons are called donor energy level, which is close to the conduction band. As you can see here, the germanium with free electrons, this is the energy at the donor level and this is the intrinsic electron at the conduction band and donated electron, this is the phosphorus ion, this is the intrinsic hole at the valency band. This is the p-type semiconductor. Again, extrinsic is divided into p-type and n-type. P-type semiconductor is obtained by doping an intrinsic semiconductor with trivalent impurity atom like boron, gallium, indium or aluminum. The 3 valence electrons of the impurity atoms pairs with 3 valence electrons of the semiconductor atom and one position of the impurity atom remains vacant, which is known as hole. Therefore, the number of holes is increased with the impurity added to it. Since holes are produced in excess, they are the majority charge carriers in the p-type semiconductors and electrons are the minority charge carriers. Since the impurity can accept the electrons, this energy level is called acceptor energy level, which is denoted by EA and is present just above the valency band. The current flow in this type of semiconductor is due to holes. This is how the p-type semiconductor is differed with the n-type semiconductor. The properties of the p-type semiconductors includes the properties, the conductivity of the semiconductors depends on its temperature and is increased with increase in temperature. The energy gap of a semiconductor decreases with the rise in temperature. At 0 Kelvin, the semiconductor becomes an insulator. The absence of an electron in the valency band of a semiconductor is hole. Hole occur only in the valency band of an empty electron state, which is known as a hole. The electric current in a semiconductor is a summation of the currents due to the electron and hole. Hole is a positive charge carrier current. The carrier, next one is the carrier concentration or density of charge carriers in intrinsic semiconductor. The carrier concentration in intrinsic semiconductor is determined by finding the concentration of electrons in the conduction band and the concentration of holes in the valency band by applying the law of mass of action. At temperature above 0 Kelvin, the two types of the free charge carriers exist in the semiconductors. Electrons in the conduction band and the holes in the valency band. In general, it is taken as a conduction band is extended from EC to plus infinity and the valence band is extended from minus infinity to EV. The concentration of electrons in the conduction band. In a semiconductor, the conduction band is completely empty and the valence band is completely filled at 0 Kelvin. Even if the temperature becomes greater than 0 Kelvin, some of the electrons in the valence band gets excited in the conduction band. So, to calculate the carrier concentration, we have to take the N is equals to density of states and Fermi function. So, after deriving all the things, we will get the carrier concentration, which is NC is equals to N is equals to NC into e power minus EF minus EC by KT from Fermi Dirac distribution. Again, in the concentration of holes in the valency band. In a semiconductor, the conduction band is completely empty and valence band is completely filled to at 0 Kelvin. If the temperature becomes greater than 0 Kelvin, some of the electrons in the valency band excited in the conduction band. So, to calculate the number of holes available in the valency band, the concentration of holes in the valency band is calculated by P is equals to density of states into Fermi function. So, we will get the P is equals to NV into e power EV minus EF by KT, where NV is equals to 2 into 2 pi mH KT by H square whole power 3 by 2, where K is the Boltzmann constant, T is the temperature and H is the Planck's constant and NV is the carrier concentration at valency band. Now, intrinsic carrier concentration. In any intrinsic semiconductor, the density of electrons is equals to the density of holes. That is, Ni square is equals to Np. So, we will get Ni is equals to 2 into 2 pi KT by H square whole power 3 by 2, Me star Mh star into whole power 3 by 4, e power minus Eg by 2 KT, where Ni is the intrinsic carrier concentration. Again, Fermi level in the intrinsic semiconductor. In an intrinsic semiconductor, the concentration of holes in the valency band is equals to the concentration of holes in the conduction band, that is N is equals to P. By substituting N and P values in the equation, we will get the EF is equals to, that is Fermi level, the Fermi energy level in the intrinsic semiconductor, EF is equals to EV plus EC by 2 minus KT by 2 log of Me square, Me by Mh whole power 3 by 2, where we will get capital E is equals to EV plus EC by 2, that is energy at valence band, energy at conduction band. Thus, the Fermi level in an intrinsic conductor lies, it forms at the center of the energy gap. Next one is intrinsic semiconductor. Impure semiconductors in which the charge carriers are produced due to the impurity atoms are called extrinsic semiconductors. Based on the type of the impurity added, it is divided into N-type and P-type. As we already studied, N-type semiconductor is doped by doping an intrinsic semiconductor with an pentavalent impurity atoms like phosphorus, arsenic and antimony. The 4 valence electrons of the impurity atoms bond with our valence electrons of the semiconductor atom, and the remaining 1 electron of the impurity atom is left free. So the current flow in this type of semiconductor is due to electrons. You can see this is the figure for the extrinsic semiconductors. Next, carrier concentration in N-type semiconductors. Let Nd is the donor concentration, that is the number of donor atoms per unit volume of the material, and Ed is the donor energy level. At very low temperature, all the donor levels are filled with electrons. With increase of temperature, more and more donor atoms gets ionized and the density of electrons in the conduction band always decreases. Ec is the bottom energy level at the conduction band, Ef is the Fermi energy level, Ed is the donor energy level, Ev is the top energy level. At very low energy, at very low temperatures, the density of the empty donors should be the same as the density of the electrons in the conduction band. This is how the Fermi, this shows that the Fermi level is exactly halfway between donor and bottom, donor level and bottom of the conduction band. This expression represents the above expression, N is equals to square root of 2nd 2 pi me star kt by h square whole power 3 by 2 exponential of Ed minus Ec by 2 kt represents the carrier concentration in the N-type semiconductor. Next, P-type semiconductor. P-type semiconductor is obtained by doping an intrinsic semiconductor with trivalent impurity atoms like boron, gallium, indium and aluminium. So the 3 valence electrons of the impurity atoms pair with the 3 valence electrons of the semiconductor atom, and 1 position of the impurity atom remains vacant, which is known as a hole. Therefore, the number of holes increased with the impurity added to it. Since holes are produced in excess, they are the majority charge carriers in P-type semiconductors and electrons are the minority charge carriers. So this is the carrier concentration P-type semiconductor. Let Na is the acceptor concentration, that is the number of acceptor atoms per unit volume of the material, and Ea is the acceptor energy level. At very low energy temperatures, all the acceptor levels are empty. With increase of temperature, acceptor atoms gets ionized. The electrons move from valency bond and occupy the vacant seats in the acceptor energy levels, thereby leaving holes in the valency band. So we will get the expression for the carrier concentration in P-type semiconductor. P is equals to square root of 2Nd into 2 pi mh kt by h square whole power 3 by 4 exponential of Ev minus Ea by 2 kt. Next, drift and diffusion. The net current across a semiconductor has 2 components. The net current across a semiconductor has 2 components, drift and diffusion current. Firstly, we will study drift current. When an external electric field is applied to a semiconductor, each charge carrier experiences a net force. So electrons move to the positive side and holes move to the negative side. This net moment of charge carriers is nothing but drift. This drift density is given by J, and J is equals to NeVd, where Vd is the drift, J is the current density. J drift is equals to Jn into Jp. We will get for intrinsic semiconductors, sigma drift is equals to Nie into mu n into mu p. Next one is diffusion. As I already told, the net current across a semiconductor has 2 currents. One is drift and another one is diffusion. The moment of charge carriers from high concentration to low concentration region is nothing but diffusion. In a semiconductor, charge carriers may move either by drift or diffusion. Under equilibrium condition, the charge density is uniform in the absence of electric field. If excess charges are given to the semiconductors by some means, the charge density becomes non-uniform. Then excess carriers move from high concentration to low concentration region. This process continues until the charge density becomes uniform, and it is called the diffusion. We will get the formula Jn is equals to J diffusion is equals to EdN into dou n by dou x minus EdP by dou p by dou x. Thus the total current density in a semiconductor J total is equals to summation of drift current plus diffusion current, that is drift plus J diffusion is given by E into N nu N into P nu P plus Dn into dou n by dou x minus dP into dou p by dou x. Next is Einstein relation. Einstein showed that the parameters which describes drift and diffusion were directly related. These two parameters are mobility mu and diffusion coefficient d. At the equilibrium, even in the absence of field, there is no current flow. Even if the electric even if the equilibrium state is disturbed, diffusion occurs at a diffusion current results in. This current creates an internal field. Thus, the internal field causes again drift current. The drift current balances the diffusion current. E mu n is equals to EdN by dou n by dou x, which is given for the drift and diffusion current due to the excess electron. And after forming the derivation, we will get dP by mu p is equals to kT by E. dN by mu n is equals to kT by E is for electrons. dP by mu p is equals to kT by E is equals to for holes. Now dN by dP is equals to mu n by mu p. This is the Einstein relation given showed between the drift and diffusion were directly related. Next one is Hall effect. The next concept is Hall effect. When a conductor carrying a current is placed in a transverse magnetic field, an external field is produced inside the conductor in a direction normal to the both the magnetic and current field. This phenomenon is known as the Hall effect, and the generated respective voltage at that point is known as the Hall voltage. Let us consider an n-type material to which the current is allowed passing on the x direction from left to right, and the magnetic field is applied in the z direction. As a result, Hall voltage is produced in the y direction as shown in the figure. We can see here this is surface number 1, surface number 2, and here the external field is applied on the x direction from left to right. Due to the magnetic field applied, the electrons move downward direction with a velocity v, causing the negative charge carriers to accumulate on the surface 1. Negative charge carriers you can see here are accumulated on surface 1, and positive charge carriers are accumulated on surface 2. Then the potential difference is given by minus EEH, force is given by minus BeV. At equilibrium both are equal, that is minus EEH is equals to minus BeV. Then after deriving all the derivation, we will get the Hall voltage VH is equals to BRHIX by W. Suppose if we want to determine the Hall coefficient, make it as subject RH is equals to VHW by IX into B. The applications of there are a wide number of applications for the Hall effect. We have listed here few applications. It is used to determine the material, whether it is p-type or n-type. It is used to find the charge carrier concentration. It is also used to determine the mobility of charge carriers. It is used to determine the electrical conductivity and magnetic flux meter or Hall voltage. Next one is the differences between direct and indirect band gap semiconductors. The first one is direct band gap semiconductor. It is impure or extrinsic semiconductor. In the direct band gap, it is a pure or intrinsic or elemental semiconductors. The examples for the direct band gap are gallium arsenide phosphate, and germanium and silicon are the examples for the indirect semiconductors. The EK curve, you can see the energy band gap curve, we can see here. This is the conduction band, valency band, and how the photons are ejected, and then the energy gap is placed between, and how this is the energy EK curve, conduction band and the valency band plotted between the E and K. The minimum energy of conduction band and the maximum energy of the valency band have the same values of wave vector. The minimum energy of the conduction band and the maximum energy value of the valence band have the different values of wave. That is, in the direct it is having the k1 is equals to k2, and the indirect it is having the k1 is not equivalent to k2. So they are the indirect band gap semiconductors are used to fabricate the LEDs, laser diodes, and the indirect band gap semiconductors are used to amplify the signals, electronic devices and rectifiers. The lifetime of charge carriers is less in direct band gap, and the lifetime of charge carriers is more in indirect band gap. The emission of light Eg is equals to hc by lambda. So there is no emission of light in indirect band gap semiconductors. Next one is PN junction diode. When a layer of p-type semiconductor material is placed with a layer of n-type n-type semiconductor material in such a way that the atoms of the p-type with the combine with the atoms of the n-type across the surface of the contact. Such surface where combination has occurred is known as PN junction diode. So p-type semiconductor is placed over the with a layer of n-type semiconductor. Then there will be a combination of atoms at one contact. Such surface junction is nothing but a PN junction. Consider a p-type and n-type semiconductors with PN junction formation is known as junction diode. You can see here these are the free electrons, these are the fixed ions. This is the junction where the layer of p-type and n-type is combined at a point of contact. The formation of PN junction diode is represented in the above figures. Let us consider the formation of sharp junction with two separate semiconductors are brought together. When they are joined in the region of contact, free electrons diffuse from the N region and combine with the holes in the P region. This is known as depletion. That region is known as depletion region. The thickness of this region is older, and due to the electric field E, the potential difference appears across the depletion region, which is known as potential barrier or barrier potential or junction barrier. And in the PN junction diode, forward bias connects the positive terminal on the p-type side and the negative terminal of the n-type side. So in the reverse bias, the positive terminal connects to the n-type and the negative terminal connects to the p-type, creating a large potential barrier. In the forward bias, as you can see, these are the effects on how the effect on the depletion region. The external voltage rushes the majority carriers, that is holes from the p-type to the electrons from the n side towards the junction. Thus the potential barrier is lowered, allowing the majority charge carriers. This diode allows the significant current to flow. The potential barrier is increased, we can see here, which prevents the majority carriers. That is how the PN junction diode is formed by combining a layer semiconducting material to n-type semiconductor material at one point of contact. That point is nothing but PN junction diode. Next one is semiconductor laser diode. A semiconductor laser diode is a compact electric component that converts the electric current into coherent laser light by using a PN junction diode. How this is working? It will work on the principle of PN junction diode. It is a semiconductor device between a p-type and n-type semiconducting material. It works in the forward bias. This semiconductor laser diode works in the forward bias. Applying a forward voltage pushes electrons and holes towards the junction. Again, in the recombination, electrons and holes meet in the junction and recombine, releasing energy in the forms of photon. This is the principle involved in this is stimulated emission. As more photons are released, they trigger the other electron hole pairs to release identical photons. This cascade creates a coherent amplified beam of light. So due to this recombination process, the light radiation, that is the photons released from a certain specified direct bandgap semiconductors like gallium arsenic, this light radiation is nothing but recombination radiation. So you can see here, this is the construction of the laser diode. The key characteristics included in this semiconductor laser diode are, it is very compact in size because they are very small and can be integrated in any types of compact devices. Especially the energy is high in efficient, they are energy efficient compared to the other types of lasers. And versatility, they have huge range of versatility, they can emit light in both visible and infrared medium. Their output can be easily controlled by adjusting the current. Most of the time they will be used in the optical communication, especially in the fiber optics to transmit the data. To store the data, they will be used in DVDs, CDs and other Blu-ray players. For the medical devices, they used in the surgical procedures and treatments. And sensing, it is works as a key component in various sensors. In the consumer electronics, it is works as a laser point. So that is how a semiconductor laser diode is used in various applications. It is a compact electronic component that converts the electric current into coherent laser light by using the principle of PN junction diode in forward bias and stimulated emission. So in this unit semiconductors, we have covered the various topics, that is the classification of solids, that is insulators, conductors and semiconductors. In this unit we have concentrated more on semiconductors, differences of differentiate the semiconductors, that is intrinsic and extrinsic semiconductors. Again, extrinsic semiconductors is divided into two types, p type and n type semiconductors. And then we have studied the carrier concentration or density of charge carriers in intrinsic semiconductors and in extrinsic semiconductors, that is p type and n type semiconductors. And then we have studied the drift and diffusion coefficients and Hall effect and then Einstein relation, and then differences between direct and indirect band gap semiconductors, and then semiconductor laser diode. This is the unit number 4 in engineering physics. Thank you.